Good morning and welcome back to the course. So we're thinking hard about life as defiance. And one of the things that I'm trying to do is to understand how the presence of some fuel leads to a dynamics that is different than, well, maybe what I should say is that it leads to out of equilibrium behavior to writ large. And I'm being intentionally vague in not saying more about that. So what I want to do here, I'm very excited about this little vignette, is I want to talk about two ways of thinking about the dynamics of a system which is out of equilibrium and how to compute what will happen to that system over time as a result of this out of equilibrium status. So we're going to examine two different approaches, one of which you're already familiar with. We had a whole vignette on it. We've used it over and over again, and that's the so-called phenomenological linear transport laws relating flux to degree of disequilibrium. And let me just remind you of that. So what I'm showing you here is several different examples. We have used the second one, the flux of molecules, because that's Fick's law. And what it says is that the flux across that area that I've shaded in green here, the flux across that can be used to compute the rate of change in the number of molecules in the left-hand box. How do we do that? Well, if I just imagine these two boxes with the partition between them, then the rate of change of number of molecules on the left-hand side can be nothing more than the number that leave per unit time. How do I compute that? I multiply the flux, which is number per area per time, by the area of the green face, and that gives me the number, the rate of change of the number in the left-hand box. Okay, so that is what I mean by the standard phenomenological linear laws. We also used this one in thinking about the frogs. So, we computed the rate of water escape due to osmotic shock. The heat equation is Fourier's law. That's also very well known and super powerful and really interesting. And then finally Newton's law of viscosity. So every one of these features the same basic idea as I showed you long ago, which is that the flux, which is number of somethings crossing unit area per unit time, or the quantity of something crossing unit area per unit time, that is going to be proportional to the degree of disequilibrium, linear in the degree of disequilibrium, with some sort of a transport coefficient that mediates the flux and the degree of disequilibrium. So, up here we saw Fick's law where the diffusion coefficient is the mediator that relates that degree of disequilibrium and the flux and so on. So that's method number one. Method number two is what I'll refer to as relaxation on the free energy landscape. And this is a very generic idea, and that is that the rate of change of the number of something or other is given by some kinetic coefficient, which, I just annotate here with this letter gamma. So this thing is a kinetic coefficient. And then note what the driving force is. So the driving force is the rate of change of free energy with respect to the parameter we are interested in understanding. Okay, so if I'm interested in knowing something about the rate of change of the number of molecules in the left-hand box, what I need to do is figure out how does the free energy change with respect to the number in the left-hand box. If the answer is that it doesn't change, we're already at equilibrium, dF by dN is 0, then there will be no dN by dt, there will be no flux. On the other hand, if we're very far away from equilibrium, dF by dN is large, and that will lead to a large rate of change in the number of particles. Okay, so that's the background. So I wanted to, just in the spirit of knowing about rather than knowing, I just want to pass along to people the idea that in the 70s and 80s there was this incredibly intense effort on the part of physicists to try to understand critical phenomena. This was on the heels of the invention of an idea called the Renormalization group. I think it was a good argument that, for the second half of the 20th century, that maybe this was the most important breakthrough in physics. It's kind of a self-conscious theory, as Nigel Goldenfeld likes to say. It's a self-conscious theory about how to make theories. And so this particular paper by Hohenberg and Halperin, two noted luminaries in the field, attempts to examine the dynamics of these kinds of systems. And, I just wanted to bring your attention to what they call Model A. And basically, what they write here in disguise is what I just said. So here you see d by dt of what they're calling psi, which is some field variable. So we're looking at a single quantity, n, which is a pointwise count of the number of particles in some box. And I said, for my purposes, I said that I wanted to think of dn by dt is equal to minus gamma df by dn. That was my hypothesis, or my proposed phenomenological dynamics. Here they generalize that. This is a generalization, where what you see is the rate of change of this parameter, this field variable psi, is given by the rate of change of the free energy with respect to the entire field. So this is a special kind of derivative known as a functional derivative. The details don't really matter for the moment. I just want to point out, this is the standard dynamics, so-called Model A. And then there's a beautiful book by Mehran Kardar called, it's two volumes, Statistical Physics of Particles is volume 1, and the Statistical Physics of Fields is number 2. And you can see right here that, Kardar is writing down a dynamics, which is precisely what I'm proposing. Forget the noise term, but deterministically, what I'm saying is that the rate of change of m with time is given by some kinetic coefficient times the forcing function. What is the force? The force is the derivative of the free energy with respect to the parameter whose relaxation is of interest. This may all seem abstract, but in the spirit of tourism, intellectual tourism, my objective here was not to teach you how to do functional derivatives. It was not to teach you about statistical physics of field theory, although that's really fantastic. It was really to motivate this idea of dynamics, so over-damped dynamics, the kind of dynamics that we would think of as a harmonic oscillator, a mass spring system, but in a super viscous fluid, or the dynamics of the flagella of E. coli. So there, the dynamics is what you might call Aristotelian dynamics. What do I mean by that? Well, it's the dynamics which says that the velocity is proportional to the driving force. So this is the driving force, and this is the velocity. So, this I can also write as dx dt. And now when I write the force here, I'm just saying that, in a way, I'm saying that the force is the derivative of some free energy with respect to x. Note here, sorry, I used F for free energy. Here, Kardar is using it for force. Okay, that's fine. We don't have to get worked up about that notational difference. The reason I call this Aristotelian dynamics is, if I take if I think about the dynamics of Aristotle, which is heavy objects fall faster, that's really what's in play here. There, the driving force, which is the force of gravity, just for example, is larger for the larger object because the force is mg. So the larger m, the larger the force. And so the thing I'm trying to say here is that, this general philosophy is really very powerful. Okay, so to see these ideas in action, what I propose to do now is to examine the so-called Erinfest dog-flea model. So what I want you to imagine is we have two dogs. Each dog has omega latticytes. I'll show you that here. So I have this is dog number 1 over here, and this is dog 2. And instead of thinking of them as columns like we did here in this figure from our 2006 paper on teaching the principles of statistical dynamics, which you might want to look at if you want, where we sort of show how you can sum over all the possible microscopic trajectories of the system. At any rate, we have these two dogs. There's N1 fleas on the left dog, there's N2 fleas on the right dog, and then the dynamics is that the fleas are going to hop, and what we want to do is we want to figure out the rate of change of N1. That's what I want to do. And the way I'm going to do this is by reckoning, we can use Fick's law, but we're also going to reckon the free energy of this little world, where the free energy is given by the number of ways of rearranging the fleas on the two dogs. And the maximum entropy state, you probably won't be surprised to guess, is when each dog has the same number of fleas. So in that case, the entropy of the universe of two dogs is actually maximized. So so let me now walk you through, and I did the calculation ahead of time because I just didn't feel like making mistakes as I did on the blackboard the other day. So the total free energy of the two planes. So I've got plane 1 and plane 2, or dog 1 and dog 2. There's omega lattice on each one. So the total free energy, I'm going to say, first of all, there is no U. And why? The reason I say that is that there's no term that says that it costs a certain amount to have a flea around. There's a total number of fleas en tot, and they're jumping around. And so the total free energy is given by nothing more than the sum of the two entropies. To get those two entropies, I recall that Boltzmann tells us that S is equal to KB log W, where this is the multiplicity, or the number of microscopic states corresponding to the macro state of interest. And here I'm invoking the fact that there's omega lattice. The omega is very big compared to NL. So let me annotate that. So this is for the case where omega is much, much greater than NL, and also n tot. That's what you could say. So, good. So this basically is the total number of ways of putting NL fleas in omega lattice sites where omega is huge. So I mentioned, before that if I think about the Rose Bowl, which is just a few miles away off my left shoulder, then there's something like 60,000 seats, and if I went over there with 20 people, the number of choices for each person is 60,000. So the total number of ways of arranging the 20 people is 60,000 to the 20,000. Sorry, 60,000 to the 20 power. I then divide by 20 factorial. That's because we people are indistinguishable. If I switch myself with somebody else in their seat, you won't know. As long let's dress us all in some sort of costume, so we're all dressed as gorillas or something, and then you can't tell the difference. So that's what this term is. That's the left box, and this is the corresponding entropy or microscopic degeneracy of the right box. And so I can simply work out what the free energy is, and it's this mess. Okay, I don't. You can work through this, and actually in the homework the students have worked through it. I worked through it already earlier when we talked about the chemical potential. It's the same thing all over again. So now I can compute dF by dN, and that's the putative driving force. That's the thing that I'm claiming drives particles. If we're at equilibrium, dF by dN is 0, and there's no drive, and that means there's no rate of change in the number of particles in the left-hand box. On the other hand, if we're not in equilibrium, then there's a driving force tending to either increase or decrease the number of particles in the left box, depending on whether the number in that left box is greater than or less than n tot over 2. So now the question is, this is the result, basically. This is the result for the drive. And notice that it features logarithms. It's not fixed law as written. It's more sophisticated. It's got nonlinearities. It saturates. In other words, as you get closer and closer to 0 and 1, the driving force basically gets bigger and bigger and bigger. It's no longer linear in the departure because there's a hard cutoff. You're not allowed to go past 1 and you're not allowed to go past 0. I guess that's one way to think about it. So what we could do is we could now introduce the idea that the number of particles on each side is n tot over 2, and then on the left it's plus delta n over 2, and on the right it's minus delta n over 2, right? The total number of particles is fixed. So if I put an extra delta n over 2 on the left side, then I've got to subtract delta n over 2 from the right side. That's a legal arrangement of the particles that respects the fact that the total number is n tot. So now I can expand these logarithms in the small parameter delta n, and what I find is that minus df by dnl gives me this very simple relationship. In other words, what do I take away from this? I want you to recognize basically that that this thing is equivalent to Fick's law. Notice that what we found is that the driving force is proportional to the gradient. It's linear in the gradient, meaning this thing. Let me do it this way. So this thing is the gradient. And then there's a transport coefficient, which has got all this stuff in it. It's got KBT, it's got gamma, delta x, and n tot. It doesn't matter because it's just a bunch of numbers. So the reality is that the drive is proportional to the gradient, the slope. Okay, so what have I claimed? What I've claimed is that we can do an exact calculation of what the free energy is as a function of the configuration. So what do I mean by configuration? Well, the number of particles on the left-hand side can run from 0 to n tot. That's it. I can have 0 particles on the left, 1, 2, 3, etc., all the way up to n tot. And so those are all the possible configurations. Each one of them has a free energy, which I can access by using the statistical physics of Boltzmann's description of entropy. And then I can compute dF by dN, which is what this curve is. That is to be contrasted with Fick's law, which is shown here. So we note that for small departures from equilibrium, say over this region, dF by dN and Fick's law tell us the same thing. But as we get farther away from delta n being small, we introduce these nonlinearities in the driving force, and so the drive becomes stronger and stronger. These things actually are diverging, at the edges. Okay, so what do I want you to have taken away from this vignette? What I want you to have taken away is the idea that a very general description of non-equilibrium dynamics, mind you, can be built around the idea of computing the free energy, but the free energy for the system when it is not in its equilibrium state, and taking the derivative of that free energy with respect to particle number or whatever other variable the free energy depends on, and that tells you the relaxation dynamics as that variable will move towards equilibrium. This is going to be very important for us when we think about the consumption of fuel, such as ATP or membrane gradients, because those gradients basically drive processes in the direction of minimizing the free energy. And so we can use precisely this dynamics. Now we can feel contented that the free energy, dF by dN, is like a generalization of the linear phenomenological laws that we introduced earlier, and in a way very much more powerful, and gives us an analytic handle that we can use in order to compute the dynamics of these systems. This, of course, causes us to broach the never-ending favored topic of when is equilibrium legitimate. It's one of my favorite topics. It's a good question. It's one worth worrying about. The thing I want to leave us all with today, without doing anything technical, is philosophical caution. To not be too dismissive. And I think I've talked about this in the past, but let's review the free electron theory of metals. Here is a craziness for you to consider. The craziness is, consider a metal as a box of electrons, a gas of electrons that don't interact with each other due to the Coulomb interaction. The Coulomb interaction is 10 to the 40th between two electrons is 10 to the 40th or 42 or something larger than the gravitational interaction between them. The Coulomb interaction is huge, and yet it's not stupidity, it's not naivete, it's actually deep, the idea that one can consider a metal as a gas of free electrons. So, what does that have to do with biology? Let's not be seduced into the idea that because we've used the word equilibrium, that means the ideas of equilibrium physics have no place in thinking about a biological problem. That's just false. That's demonstrably false. And it's demonstrably false in the sense that you can actually make measurements. I'm not saying it's always true that one can do it, but there are cases in which you can. And it's worth understanding what that's due to. And one of the fundamental statements that I will make is it has to do with separations of timescales. I wanted to just also say, let's resist this idea to have a knee-jerk reaction against equilibrium on the grounds that, for example, when we think about degree of ionization, I've already mentioned this, but degree of ionization of atoms in a star, A star is a pretty non-equilibrium place, and yet there's an equation known as the Saha equation that uses the Boltzmann distribution, and it allows us to compute the degree of ionization. In a sense, as an equilibrium thing. Similarly, if you even think about something as crazy as an atomic explosion, the treatment of the gas inside of the explosion can be locally thought of using local equilibrium ideas. My point is that we can get a lot of mileage out of the out of equilibrium free energy. What do I mean by that? You have a free energy which depends on some parameters, and if you choose those parameters such that the system is not in equilibrium, you still can compute the free energy. And I think I don't know if I had it here, but maybe I have it here. Yeah. We did this already. So basically, this is a free energy curve. The green curve is a free energy curve. I mean, it's really the entropy, but I multiply it by temperature, and that's going to give me the free energy. I need to change the sign, so it's going to be a curve like this. But that's the free energy even for the case where I'm out of equilibrium. In other words, for all the situations, I can use these ideas, and I consider it a very interesting point, which is when do you have to even abandon that? And that's a debate for another day.